we should be live. Double check.
I am checking right now. Usually takes like a little bit of time. Yep, we're live.
All right. Hello and welcome everyone to Corecast. I am your host, Tim.
Mikey.
This is Sahil. Welcome, everybody, to a brand new exciting episode of Corecast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern. Do ask us questions during the episode. We'll get to it. So, without further ado, let's get to it. So, Tim and Mikey, this is an interesting episode. We've talked about it, sprinkled it here and there, but essentially, I'll just ask you straight up, like, what do fractals, which is this abstract mathematical structure, have to do with particles? Like, why is that even important? I guess, Tim, I want to point this question to you first.
Yeah. So I I think the concept of fractal mathematically kind of seems tantalizing. We learn about these beautiful objects like the Mandelbrot set, the Sierpinski triangle. I think maybe mispronouncing it. Um, at the beginning, at face value, it doesn't seem like it has anything to do with physics. Although in popular science, we see sort of like repetitive structure. Like the planet orbiting the sun and like electrons orbiting a proton. But these are not really fractal-like structure in the mathematical sense. These are just kind of tantalizing hints that they are fractal-like structure, at least a little bit in nature. But it turns out that in particle physics, when you go to higher and higher energy, particles sort of start to lose their identity a little bit. And if you look into, if you try to really probe a particle, you start getting these recursive phenomenon, and as we'll describe later, and that also shows up in the different parts of mathematics around our particle physics, like Feynman diagrams and whatnot. You see these intricate structure that kind of looks like a fractal, and it turns out that it has physical consequences. And at the end of the day, it digs into the heart of what it means to be a particle, and it becomes kind of ambiguous now. It turns out, and I think part of it is a bit of a surprise that it has a role in particle physics, and it also seems to be fundamental at some level to what particles are.
All right. I mean, I'm excited to get into this. Mikey, question for you. Tim has mentioned the word fractals many times. What does
Yeah.
that even mean? What is a fractal? Let's
Yeah.
lay the groundwork.
Yeah. I mean, I don't know. I guess I would take a slightly like more like what's the word? Amicable view than Tim about like how the fractal nature of the universe, because I think he gave one of the best examples of what a fractal really is. And it's like, I think everyone when they learned about the solar system, planets orbiting a sun, and then they learned about the Bohr model of the atom. It looks like planets orbiting a sun. You zoom out to galaxies, there's a black hole in the middle. It looks like planets orbiting a sun. So on all these different length scales, from galactic to planetary to atomic, you have structures that look the same. And um, if the pattern repeats exactly, then you would call that a fractal. If literally, like every time you zoom in, like you get planets and you zoom in and atoms are just like planets. And if that were true, then that would be fractal. Um, but just because something is not perfectly fractal, it doesn't mean that it's not fractal. It is. You can measure how fractal it is. How much does it repeat itself as you zoom in? And this is a quantifiable number. You can calculate the fractal dimension of the galaxy. You can calculate the fractal dimension of the solar system, and it's quite high. It's quite high.
Mhm. Anything you want to add to that, Tim, about how you think about fractals?
Yeah, and I think there's a distinction between like exact fractals, like the Sierpinski triangle. Like if you zoom in, it looks exactly identical. Like we're not talking about that. Nothing in physics is really exact. We're talking about maybe there's some similarity. Maybe it's not exactly the same, but it's simple enough that it warrants some kind of a discussion, you know. And I think one good example is sort of the coastline. I think the classic example is like the coastline of Britain or something like that. Like on a map, you see these squiggle line along the coast or the California coast, right? And there's a question, you can ask the question, well, what exactly is the coastline of California? Is it the squiggly line on the map? But then when you zoom in a little bit more, that squiggly line has just gotten more squiggles. You know, like what you thought was the original coastline, when you zoom in, it becomes more jagged. And if you zoom in some more, it becomes even more jaggedy. And of course, if you look at the atomic level, the coastline is not really a well-defined object, right? You go to the beach, like where in the sand do you draw the coastline? I mean, the water is coming in and out. It's always changing a little bit.
Is that really special to Great? Is that really special to Great Britain?
Probably not. It's just an example, right? I think people.
Yeah.
That's fair. So one question I want to ask, just to kind of give a bit more geometrical intuition behind this, because Tim, you mentioned a special kind of triangle. If I take a 1D example, is if I take like a line segment, let's say it's of length 1, and I remove the middle third of it, and then I have 2 line segments, each a third of a size, then I remove the middle third of those, then whatever's remaining, I remove the middle third of those. Would that be a fractal-like structure?
Yeah.
Isn't that a one-dimensional Sierpinski carpet?
I think so. I mean, Sierpinski triangles where you have a triangle and then you break it up into 4 triangles, remove the middle one, then you have 3 triangles, and then you remove the middle, like you break that each of those 3 triangles into 4 triangles, smaller ones. You remove the middle one, and then you just keep repeating the process. And so, for those of you interested, Wikipedia has like a good illustration of this that's easier than me explaining in words.
Let me just add that, sure, we have these really intricate examples of what a fractal is, but actually some fractals are very simple. For example, a line is a fractal. You zoom in a line looks like a line. Like you zoom in a line still looks like a line. Or like empty space is a fractal. Even if you ignore quantum physics, there's nothing. You zoom in, there's still nothing, right? It's a fractal, but it's like the most trivial form of fractals.
Yeah, it's a trivial fractal.
That's a great example. Okay, so it seems like fractals have this, like, we talked a lot about zooming in and zooming out, and kind of, I mean, effectively looks the same whether you zoom in, whether you zoom out. And even I've heard even like stock market signals can be said to be like have fractal-like nature. Like if you take like let's say a particular stock or S&P 500 or whatever, and I were to like give it any 2 times and hide the y-axis of what the value is, you could not in good faith tell me like what time period it really is, because it just looks all over the place. Apart maybe from like extreme events where it goes up or down, like very viciously, but overall. So that's a more realistic example where I've seen fractals come in. So we've talked. So anyway, coming back to this, we've talked about it zooming in and zooming out. So in the process of zooming in, what does this have to do with particles? Like how? I mean, can we talk about what it means to zoom into a particle, and where does this fractal-like nature come from? So I guess Tim, go ahead.
Yeah, I think we talked about many times in quantum physics. Kind of gives you this concept that in order for us to see something, you have to perturb the system, and that's fundamental to quantum physics, right? Like in order for you to make an observation, you have to tweak with the system a little bit. And in practice, what that means is, imagine I have an electron and I want to see where the electron is. I want to see what that electron looks like. You have to choose a particle, let's say a particle of light. And in order to zoom in order to see the electron, you have to throw some energy at it, to play with it, to interact with it, And in quantum physics, there's a famous relation, it's a very rough relation, that says the smaller you zoom in, the more energy you need to do that zooming. And we can explain that in a bit. And that means that zooming in quantum physics means higher and higher energy.
Gotcha. Mikey, can you give
Yeah.
some basic intuition behind why if you zoom in more, do I need to go at higher and higher energy, or what does higher and higher energy mean?
Yeah, so uh I guess this is the analogy we used last time, right? Like suppose you
Mhm,
have um like oh gosh. Suppose you have like a bunch of like baseballs glued to a wall.
mhm,
Um if I wanted to probe the structure of those baseballs glued to the wall, I would throw marbles at it, let the way marbles scatter off. And based on the way the marbles scatter off, I could deduce, oh, there's some spheres here, because sometimes they're bouncing left, sometimes they're bouncing right, sometimes they bounce straight back. I could basically
mhm,
like piece that together. Um, if I try to throw beach balls at the wall, that's covered in baseballs, then I'm not going to get any information at all because it's just going to bounce back. It's going to be insensitive to
mhm,
tiny details. And so that's the idea, is that when you want to probe something small, you need to use something small. And
mhm.
in physics, things that are small are very energetic. There's no way around that. There's an inverse relationship between size and energy. Um, so it's kind of like, yeah, there's not there's no current known way to get around that dilemma.
Gotcha. You want to add anything to that, Tim?
Yeah, no, I think that's it. That's the fundamental relation that quantum mechanics introduces.
Yeah, and just to throw a little bit light on this to expand upon what you're saying. So in actuality, the way people do experiments is by throwing light on an object, and in order to get at a more granular, not granular, a finer resolution of detail, you need to have a photon that has has a shorter wavelength, meaning more wiggles. And so having more wiggles increases the frequency, and frequency and energy are, basically proportional to each other. And so the higher the frequency, the more wiggles, the more energy. And so thus, if you want to go at smaller and smaller scales, you need to send a higher frequency photon at it. Is that essentially the argument?
I
Yeah,
would say
that's
that's
but
exactly correct.
yeah. Eh,
Okay, great. Yeah. Oh, good, Tim.
Yeah, I would say that it doesn't apply just to light. You can use electrons to probe an object. You can
Mhm,
use protons to probe an object, or neutrons even.
mhm.
You always just need more energy in order to probe smaller stuff.
Okay, that makes sense. So now that we've described like what it means to zoom into a particle, meaning you want to see the finer details of the particle, meaning you have to increase the energy of your interaction, whatever you're sending, to examine the structure of that particle. I guess, Tim, can you walk us through like, the different levels of like, as you throw more energy, like what will you see? What will happen? Say we have a device that can generate a near infinite amount of energy, or a really high amount of energy, not infinite, but you know, much higher than we have right now. What would you
Yeah,
expect?
yeah. Basically, imagine in real life. Let's say you want to zoom into an electron. So the more you zoom in, the more energy you put in. And because of Einstein's theory, probably the famous equation E equals mc squared, it tells you that if the more energy you zoom in, that energy becomes available to turn into mass. You know, and for
Mhm,
example, if and this actually doesn't happen in everyday life. Like imagine I want to look at my hand, right? And I might send some light at it, and usually the light source is our sun. Our sunlight doesn't have too much energy, and I can see it. So nothing dramatic happens, right? And it's
mhm,
because those light is pretty low energy. Visible light doesn't have a lot of energy. But if we increase that more and more by zooming in, eventually there's enough energy to actually create new particles like electrons and protons even, and you could even have enough energy to create a new hand out of the hand that I'm observing. Like that's the amount of zooming in we're talking about. Like when you pass the threshold when new stuff is allowed to be created, this is when you start to see the fractal structure come to life, basically. Because the more
mhm.
you zoom in, the more stuff you get now. This is kind of like a real life Sierpinski triangle, and it's really kind of remarkable if you
Mhm.
think about it.
So let's walk through the case of an electron. Say I have isolated an electron, and now I want to like zoom in more and more into it to see like, is electron truly fundamental? So I just keep throwing more energy at it. What happens to that electron?
Yeah, I think the the first thing you see is if you try to zoom in, initially there's not much, right? The light becomes more and more intense. If you get closer and closer to the electrons, the electric field might get more intense. You might feel some magnetic interaction as well. But the moment you start passing through the zoom level that correspond to, let's say, the mass of an electron and positron pair, all of a sudden, they can pop out in the vacuum. And now, instead of seeing an electron, you have a chance. Let's think for a moment. Imagine there's an electron there. You zoom in, you pass that threshold, you might actually see an anti-electron, a positron. Or you might see another electron, or you might see multiple electrons. Because more and more electron particles are able to just kind of pop into existence. And the more energy you put in that system, actually it gets more dramatic. When you pass through different kinds of threshold, not only would you see electrons, you actually see other particles now. You might even see a proton if you put in enough energy, or some other particles that people might not be as familiar with, like a muon, or like quarks, pions, and so you actually see a lot of stuff, potentially.
I'm thinking of a stupid analogy in my head. I'm wondering if Tim thinks that this is okay. I don't know why this just popped into my head. It's like, I'm like imagining, like, suppose you're like, put a pot on the stove to boil, and you want to locate the first bubble that pops up when the thing starts boiling. Well, if you want to locate the bubble, the bubble from, the first bubble from the boil, you need light. So you can shoot a laser at it. So you win if you can shoot the laser at the bubble. But as you try to do this, you find that when you shoot the laser into the water, it boils the water itself and creates more bubbles. And so you lose track of which bubble you're looking for because looking at it just creates more bubbles. I feel like that's wrong, obviously, but it feels like philosophically correct to me at the moment.
Yeah, I think that seems like a reasonable analogy.
Yeah. I mean, obviously it has its weaknesses, but just like the feeling that's how it feels to me.
I think you've gotten Tim's approval on this one. Yeah. Okay. So as you zoom in with enough energy, you can just create pretty much particles pop out of existence, like actual real particles will just pop out of existence. Like from an electron, you could get a bunch of other electrons and positrons that are around it. You can get protons, maybe an anti-proton, and like all sorts of other particles in the in the standard model and whatnot. So the question is like, if I keep doing that, let's say I have the capacity to keep increasing the energy, like can you describe what happens even more? Like just what happens?
Tim can do the honors.
Yeah, I think as we mentioned, as you increase the energy more and more and more, this fractal nature becomes more and more apparent. Like initially, when you zoom in, you're not able to see anything extra. And by the way, you can ask, where the hell is that energy coming from? And I just want to reiterate that. It's coming from the observer itself, basically. Because in quantum physics, there's no way to observe without you messing with the system. And let's say you zoom in on a level really small. Let's say you have 1,000 units of energy to shoot into the system to observe it. Maybe 1% of that will just go to creating other stuff, And the higher energy you have, the easier it is, because the small amount of fraction of the energy you put in is needed to create new particles, right? So as we zoom in, you actually see. I guess if you kind of do this thought experiment, it's kind of amazing because the more you zoom in, the more energy you have. You almost kind of going to the beginning of the universe. You see more and more types of particles getting potentially created. I think first is the electrons. And then pions, and maybe some quarks. And then as you zoom in more, you might even start to see some of the particles that people might not be familiar with, like W and Z boson, or the Higgs boson, maybe the top quark. And if you zoom in even more, you probably start to see particles that we have not even discovered ourselves, and so on and so forth, right?
Mhm. Yeah, I actually, one question I want to ask, I've been kind of taking this for granted, but why is it that like with enough energy, particles will just pop out, into existence? What, what governs that? Is that just randomness, or is that just a postulate of quantum mechanics, or I just don't want to take that for granted if there's a deeper reasoning behind that.
Yeah. That's, I mean, that I would say that the one and only rule in quantum mechanics is anything that can happen will happen. And what determines what can happen is how much energy is there, right? Like what determines my buying power is how much money I have. In the same way, what determines what can exist is determined by the amount of material, the amount of starting material you have, which is the energy. Um,
Mm,
so yeah, I think we kind of just have to take that as a postulate of quantum mechanics observation. Every single observation that's ever been made supports this idea that like quantum mechanics is a set of rules, and anything that's in the allowed possibilities will happen with
Yeah,
non-zero probability.
I would kind of flip the question around, right? I think that
mm,
the puzzling aspect is not that, oh, how come all these crazy interactions happening. The puzzling aspect is actually that how come our world is so calm? Like we have
Yeah,
we
mm.
have quantum mechanical particles all over us, and like
yeah,
when I see my hand, I don't start like a nuclear reaction. I can like exist peacefully, and part of that is because in some sense our world is very energy poor. We're kind of like we're just barely scraping by. There just isn't enough energy to do very much. And I think quantum physics itself is very what's the word like it's like a multi-billionaire. It's very willing to spend energy wherever possible. It just throws energy in all kinds of places. Like, and you can see that like we have observed like very very high energy particle from outer space, like from
Mhm.
these might be coming from galaxy centers that are very active, cataclysmic events from outer space, and when these particles come in through the from the outer atmosphere into Earth, the effects are dramatic. Like what people don't realize is that when we observe high energy particles, we don't just observe one. They do what we call shower. It's just like the particle might split into a few other particles. Those might split, and that itself is kind of like a fractal structure. It's almost like a lightning bolt that just split and split and split and split, right? So one particle coming into the atmosphere will create a whole mess, a web of showers coming in. Like that should be the status quo. Like most particles in the quantum realm, when they have a lot of energy, they go crazy. They just go crazy, right?
Interesting. So what you're saying is that if you have like a particle that comes from space, really high energy, it will just randomly split because it has enough energy maybe into two other particles, and then those particles will split and forms this like kind of nice fractal-esque sort of thing because of the splitting.
Yeah, exactly. Exactly.
Okay.
yeah. In fact, the
Okay.
splits are fractal, right? What is that? The D-glass?
Um, so I guess that ties it back to like the reason we don't see this in our everyday life, like particles popping in out of existence, is because we're in a very low energy state, essentially. Like creating these particles is a huge cost associated with it. And so it requires like particle accelerators and whatnot to have a reasonable chance of even seeing these.
Yeah, I feel like we're living in a tank full of cold water, and in cold water, you might see a bubble, and a bubble might
Mhm,
seem like it has some permanence. It just stays there, and you can
mhm,
give it a name, you can talk to it. But then once you
mhm,
increase the temperature a little bit, that bubble no longer has a name. You can't distinguish it from the other bubbles. It's turning into two
mhm,
bubbles, turning into three, turning back into one.
mhm.
And can't give it a name.
Oh. So going off that analogy that you mentioned, actually, that's an interesting analogy. Where if you have an electron, going back to our electron experiment, you shine light at it at a high enough energy, you will then lose track of where it was. I mean, I know in quantum mechanics you can't label particles, but just for the argument's sake, say you had one electron, you keep shooting energy at it, it'll become many particles, and you won't know, oh, which electron am I keeping track of? Like where
Yeah,
is everything? And it
it's
just
not even a
becomes a
well-defined
jumbled up
question.
mess.
Yeah, they're literally
Okay.
what you thought was an electron was actually two,
Mhm.
3, 4, infinite number. It was a mistake
Oh,
to think that there was just one there. It had a lot of
how?
partners that weren't showing their faces.
So one question I do want to ask is that conservation of charge will still be there, even if I take the entire
Yes,
sum
yes,
of everything, they'll still have a
yeah.
negative charge.
It
Okay.
has to be
All
it
right.
has to be an odd number.
Okay. I see. I see. Okay. So now the main question I have is that can you do this forever? Like, can you keep just pumping more and more energy? Like, what's gonna happen? Like, just say I have now an infinite amount of energy or near infinite amount of energy available to me. Can I keep doing that? I guess Tim, I'll point this question to you.
Yeah, and like many of other episodes that we have done so far, the answer is always no. It turns
Same.
out.
Oh, and the answer is
So
always the same. You always end up with the same thing.
yeah, and you know, and that end result is actually what makes particle physics very interesting. Like let's say your goal is to trying to catch that electron. You know, you're like, I'm gonna chase after it. I'm gonna zoom in more and more and more. You shoot more and more energy. You see more and more particles, and yet, let's say you're not giving up. You're like, I'm gonna find it one day. But lo and behold, at some point, gravity becomes important, and then I think this fractal structure kind of comes to a halt because
Yeah, for sure.
Mm.
at
What do
some
we call
point
that? It's called a there's a word for it, right?
the black hole
Crush.
basically, right? Once you
Yeah.
have enough energy sending into a system, you zoom in, you make a black hole. And then the thing about black hole is the more energy you zoom into the black hole gets bigger. So your resolution gets worse and worse and worse. So there's kind of this turnaround curve, right? You see this fractal structure getting crazier and crazier until you hit a black hole, and then all bets are off. You know, because
And
you
everything just
can't.
erases.
Yeah. And then you kind of go back to the original goal. You can ask the question, well, where was that electron that you were looking at? And that really mess with philosophy a little bit. I think, like, where is that particle? You know.
So as you keep shooting more and more energy, eventually you reach the point where gravity becomes important. You create a black hole. Let's say you're like, okay, you know what? I want to see what's inside the black hole itself. So you throw more energy, it just creates a bigger black hole. So you can't. There's no more to go, basically.
Yeah, basically, when you create a big enough black hole, the observation become part of the system. You are part of the black hole. Like you were trying to do an experiment, but you become one with the black hole, and you're never going to extract information out of it. If you fall
Hey,
into it,
Tim.
yeah.
Sorry, not Tim. Okay. Quickly after.
Go ahead, Tim. You'll ask after.
Oh yeah, I lost my train of thought. Yeah, sorry.
Oh.
I think quantum mechanics throws a wrench and tells you that you cannot perform this experiment anymore. There's like a threshold at which you can resolve the system, and that is, you roughly the Planck length. You know, the energy is roughly the energy required to turn the particle into a black hole. They're all equivalent, and this is where the game ends, basically.
The final boss of the universe.
The black hole essentially is what you're saying,
Yeah,
Mikey. Ah,
exactly. Tim,
okay.
did people used to call this something like the cosmic censorship hypothesis or something? That name just popped into my head.
Maybe I thought that had to do with singularities never exposed, but that's a digression. I'm not
No,
sure.
That's similar. It's like you can't actually probe structure this into singularity. But yeah, basically the idea is like black holes represent like a point at which, um, I guess, according to modern physics theories, they call it the cosmic censorship hypothesis because you can't know anything beyond that. Um, yeah.
Yeah. Well, then, so I guess this ties well into an audience question, which I think you answered, Tim, is that the Planck length is the limit for fractalization of particles. Is that correct?
Yep.
Yeah.
Yeah.
Okay.
So
Yeah.
let me just add a little bit of the context, right? So because we don't understand quantum gravity, and part of the reason is because of this black hole issue, uh, people have tried to maybe build quantum gravity theories where gravity is kind of like a fractal. Um, but I don't think any of them has been that successful.
What are they called? Does this program have a name
Is
that I
it
might recognize?
like conformal gravity, something like that?
Yeah, I've heard that before.
Yeah, but I don't think it really works because yeah,
Never heard anything of. Come
yeah.
out of it.
Basically, the idea is that I think the problem with programs like this is that fractal-like structures certainly exist in the universe, but they're not really that fundamental. Like I don't think nature requires the world to have similar behavior. But because of the nature of quantum physics and combining that with Einstein's theory, you naturally get these fractal-like behaviors. Because quantum physics, anything happens can happen, and the math is somewhat similar, and you
Well,
naturally
let's say in physics we like fractal structures because if it's fractal, then we can calculate it. Um, so we like it's a important conceptual limit, which we can compare real life to in some situations. But
yeah.
you take it too far, I don't think you're gonna find any fruit.
Yeah, so yeah, just to reiterate that caveat, the fractal nature of our world is only approximate. You know, it's like a piece of fern or like what is it, one of those cauliflower, right? There's a limit. There are always some limits to how much you zoom, how similar it is, similar it is, and how much you can zoom in. But still, you know, it is still a useful tool to consider.
Yeah. And then, Tim, you were also, I mean, you didn't mention this, but in discussion for this episode, you actually mentioned this actually relates back to the example of the coastline in Britain, that if you zoom in enough, like, where does the coastline go? Like, you can, you go to a certain length scale, you see the coastline, and then if you zoom in, it's kind of like, oh, where does the water start and the land start or end, or, is that a fair
Yeah,
statement?
that's exactly the same philosophy, you know, and this really is this really is one of the key lessons here. It's like we exist, you know. Of course, my hand is made
Mhm.
of protons and electrons and neutrons, you know.
Mhm.
And loosely speaking, I know where my hand is, but just like the coastline of California or UK, it's only approximate. It only makes sense insofar as I'm not zooming in super close, right? And and because of this thought experiment, you know, there's a limit to how much you can zoom, and the more you zoom in, the crazier it gets. Like our existence, everything that we know and love, everything that exists, is just kind of like a zoom out average view, just like the coastline. I think the analogy is apt.
Yeah, I like that analogy a lot. There's another audience question I want to ask. Is virtual particles appear in perturbative treatment of quantum mechanics? What about non-perturbative formulation? Uh,
Great question.
Tim, I'm going to point this to you.
I think it is.
Great question.
I think we had somewhat of that debate in one of our other episodes about virtual particles. There are two viewpoints. I think you can think of it as a complete artifact that doesn't mean anything, and certainly maybe there are different formulations of quantum physics where this is totally useless, like you don't even need it. But I don't think you can completely define quantum physics without what we call perturbative treatment.
Yeah.
That just hasn't been done. And also, you can also argue that all the particles we see, they are not as real as you think they are. You know, they only exist. Like for example, my hand exists. The protons in my hand exist, but for how long? We know that the virtuality, how virtual a particle is linked to its lifetime. A particle is definitively real only if it lives forever. But as we all know, nothing lives forever. Even the universe is only, what, 13 billion years, give or take? The protons in my hand hasn't lived forever yet. So we don't even know if these are like real particles. So all of us has some level of virtuality in it. And if you add in this black hole issue, like it just throws another wrench in it further, right? Like nothing is exactly real or exactly virtual. So I don't know where exactly you draw the line. So I think it's not exactly useful to draw these distinctions. Like if virtual particles give us utility in understanding the world, you know, why not use it? Yeah.
Yeah, that's really what it comes down to, right? Like, so as the as the viewer correctly pointed out, there's this kind of like tension in physics because we don't actually know how to calculate anything exactly. We can only calculate things approximately, and when we calculate things approximately, they look like particles. When we do this perturbative expansion, it produces in the mathematics, you get these objects that look like particles that we're familiar with. But again, these are only approximate answers. And so, as the viewer correctly points out, there's a large program to try to get away from these approximate answers, try to get some exact answers. But the funny thing about that is that when people try to do that, they find that the answers are sort of the same. Like when you look at non-perturbative physics, you can define particles in a completely different way, but they actually map the same particles of the perturbative physics equation all the time. And so this is one of the examples of like what modality physics we talk about. So the relationship between like the perturbative particle description and the non-perturbative particle, I would say it's still a little bit murky, but it's definitely one of those active fields of research.
Yeah, that makes sense. I appreciate the answer from both of you. So we're almost at time, and so I mean, Tim, you were answering the question about like, so if you had to actually before we do that, Tim, if you had to bet money, would you say gravity is a fractal or not? Like has a fractal-like structure rather?
That's I don't know where I would place the money because because we know so little about gravity. I would say because in recent research we know that gravity actually has a lot of similarity with other forces. So I would probably say that gravity has some level of fractal-like structures. I probably would bet money on that. But whether or not fractal-like structures should be a fundamental principle for gravity, that's probably no, right? Probably not.
Yeah. It's a useful tool for understanding things, but it's not the end all be all.
So actually, one question I have, maybe it's a bit reductive, but I mean, if something is a fractal-like structure, couldn't you say it's like more, like it's a more efficient description of it? So of nature
Hey,
itself.
you're taking away my closing argument.
Oh,
That's what I was gonna say.
Okay. You know what? I'm
kidding.
Okay. Oh, damn. Okay. I don't know if I should ask that question anymore. I'm taking your thunder away. I guess.
Well, that's okay. Like, just like, actually, I just thought of this like during this conversation, but it's like, okay, so we talked about how fractal means like as you zoom in, you get like a repeating pattern, right?
Yeah.
So I thought like, what will it mean to be non-fractal? It means every time you zoom in, you get something completely new. I don't think the universe has that kind of infinite variety. There's got to be, you have to reuse the structures at some point, right? It can't be like, if you only use it once and you never use it again, that's crazy. That's like super inefficient, just as you point out. So I'm of the opinion now that like some degree of fractal-like nature is inevitable. Like you can't have that much novelty. You can't see something that new every time you zoom in, right? The universe isn't that creative.
That's fair. All right, you know what? I think that that answered my question, even though I didn't fully ask it. But yeah, so I'm going to, we're almost at time, so I wanted to give you guys a chance in our tradition we always do to give any, final words or closing thoughts or words of wisdom that fractals and particles having fractal-like structures approximately have taught you. I guess Tim, you go first since Mike.
No, I went already.
Oh, okay.
I would say that like initially we're talking about an object that are so simple, a single particle, and I'm sure like back in the days before the event of quantum physics, relativity, people also thought back in the days like Poincaré, the classical physics era, right? They thought when they can calculate movement of particles, that was all there is to physics. That was it. You calculate how particles move, and that's it. And now we're discovering that, look, what you thought was just a dot, an infinitesimally small dot, actually has an infinitely, almost like self-repeating to some level, structure that is just not easy to describe at all. And it's And I think it's
Not
another story.
obvious. Not
Yeah.
obvious at all.
It is completely non-obvious, right? Like people don't exactly expect this. But I think it's another example that of it's another example of when the universe like humbles you. You know, like even things that you take for granted, like existence, just like the fact that they're particles, and the fact that we are who we are, that is all because we live in this cold, low energy world. And the moment you move away from our little bubble of universe that has that experience, you realize that man, the reality is far crazier than what we thought. Yeah, so I think I think it's something to appreciate that actually we are not fractal-like. That's why we are special. We're unique. You know, like you zoom in to me, Tim, you don't see more Tims coming out. There's something special about that. I think.
I mean, isn't that possible though? At some, I guess, can that
Definitely not
happen?
impossible. It's not impossible,
Yeah.
for sure.
I guess, well, Tim, in that example, like to have more Tims come out means that you have to have like a certain arrangement of particles to come out of you. But if you're going in that close, like, does Tim even make sense anymore?
Probably not.
Does you as a concept
Yeah.
make any sense?
At that level, I would just be like, I don't know, a hot plasma. There will be no interesting conversation coming from tin. There will be a lot of nuclear reactions, high energy,
Yeah,
the nuclear reaction. So
I see.
Yeah, we can all appreciate the context-dependent nature. The context thing. Very context-dependent. What is Tim?
So actually, one question I have is that we do see even approximate fractals arise from low energy states, right? It's not just even at high energies when I probe particles, I see this fractal-like structure. But as you're mentioning, Tim, like a fern or like even a coastline or like maybe a piece of broccoli, for instance, those are all approximate fractals. So I guess is there any like deeper connection between like the low energy fractals that we see and like the higher energy ones that
yeah,
we described in this episode?
I think that the explanation for those are fundamentally different. Those are what we call sort of emergent symmetries. I think we covered some of that in previous episode. And there's an explanation for it, but probably it's too much to get into. I think we refer to the viewer to one of our previous episodes on symmetries.
All right. I like the plug for our episode. Okay, so well on that, Mikey, anything you want to add before we
Nah,
call it a
nah,
day?
nah.
Okay. All
We're
right.
good.
Well, I'm glad I stole your thunder this time.
Yeah. Well, you're a prophet.
All right. So on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all. Bye bye.
Yeah. Bye.
Bye.